Hello everyone. In our last lecture, we started unit second, which is focusing on the various laws of thermodynamics, right? In the last lecture, we have studied all the definitions, basic definitions about the systems, surroundings, and also we have learned about the work and energy definitions and their if they are path dependent or not, right? And we have also seen about the zeroth law and first law of thermodynamics. These were very important, as I told you in the last lecture. These are very important and we can apply these to our daily life also. There are a lot of applications where these laws are applicable. From today's lecture, we will go to see some application which can be applied using first law of thermodynamics. So the objective of today's lecture is to understand the applications of first law of thermodynamics, and the outcome will be very similar, that you will be able to learn the implementation of first law of thermodynamics to various systems and conditions. We will consider one by one different conditions, different systems. Okay. To achieve the objective, I have divided today's lecture into few topics. The main topic, or we can say the major topic of today's lecture, is applications of first law of thermodynamics. That is divided into several parts depending on the different condition. The first condition is specific heat of gas, and we are considering here the specific heat, or we can say the internal energy, as a function of V and T. So we are taking V and T as independent variables. Secondly, we will see about isochoric process. The third one, we will see about isobaric process, and lastly we will look onto the expression for adiabatic process. If you remember, in our first unit we have already seen the expression, the relationship between the variables for adiabatic process. But here, that time we have used different theory to derive the expressions. But now, in this lecture, we will derive the expression for adiabatic process using first law of thermodynamics, because we are studying here now the applications of first law of thermodynamics. Here are some reference books you can use to study further. There are some books from Indian authors, and first book is from the foreigner author. So you can consider any one of these. All of them are very simple and easy to understand. So let us start with the first topic, the application of first law of thermodynamics, and subtopic is we will calculate the specific heats of a gas where V and T are independent variables. Okay. Now we have already seen that the internal energy of a system is a single valued function of state variables, right? I.e., that means the pressure, temperature, that means the pressure and temperature or any other variables, they can be considered as a state variables, right? Now, if we consider the case of any gas, out of these variables, any two variables are sufficient to define its state completely. I mean, we can define the state of any gas using pressure and volume, using volume and temperature, or pressure or temperature. So the two variables are enough to define the state. Here we are considering that V and T are the variables which are defining the state of any system. In that case, what will happen? The internal energy is considered as a function of volume and temperature. Let us consider this as equation 1. Now, since U is a function of V and T, we can write this equation on differentiating in the form of one term will be with respect to volume and one term with respect to temperature. So that we have written here, the du will be equals to del u upon del t at constant volume into dt plus del u upon del v at constant temperature into dv, and that we have nominated as equation number 2. Now let us consider if an amount of heat delta Q is supplied to the system, and because of that the volume is increased by dV, right? In this condition we are keeping the pressure as constant. As we have seen, we have already assumed that B and T are the independent variables. So we are considering here that B and T are getting changed. T is changed because of delta Q, because of we are supplying that, and we are keeping the pressure constant. Right now, if you remember the last lecture, we have defined the first law of thermodynamics is del Q equals to du plus del W. Right? We have seen these two are different kind of differentiation. This is perfect differential and this is not perfect differential. Right? Now, if we consider this term del W, what is that? That is given by the multiple of P into dV. So we can replace this term as P into dV. Final expression will be equals to del Q is equal to du plus P dV. Now, if we substitute the value of du from equation 2, we have already get the value of du. If we put this value in this equation, what we get, del Q is equal to del U upon del T at constant volume into dt plus del U upon del V at constant temperature into dV plus P dV should be as it is. Now if we divide it both sides by dt, so we are taking this dt somehow on the in the denominator of left hand side. So we are taking this del Q upon dt equals to del U upon del T into V plus del U upon del V at constant temperature into dV upon dt plus P into dV upon dt, right? If we rearrange it, you can see here that this term and this term is common here. We are rearranging del Q upon dt equals to del U upon del T at constant volume plus bracket P plus del U upon del V at constant temperature into dV upon dt. Let us assume this as a equation number 4. Now, if there are two cases, one is if the gas is heated at constant volume, and second is if the gas is heated at constant pressure. So first let us assume that gas is being heated at constant volume. How to define that? The del Q upon del T at constant volume is already defined as Cv. Yes, in the last lecture we have seen that specific heat at constant volume is given by the heat change at unit temperature change, right? So we can write this as Cv, and since the volume is constant, what will happen? This dV upon dt will become 0. So if we put these values in equation 4, what will happen? Del Q upon del T, we can write this del Q upon dt at constant volume equals to del U upon del T at constant volume equals to Cv, because this term becomes Cv and this term becomes 0. That means Cv we can write this value ultimately, right? Now we consider the second condition. If the gas is heated at constant pressure, from the definition of specific heat of gas at constant pressure, we can write Cp equals to del Q upon dt at constant pressure. Now putting this value and the last value in equation 4, it will become Cp equals to del U upon del T at constant volume plus P plus del U upon del V at constant temperature into del V upon del T at constant P. Now we are changing this value to Cv plus this value as it is, this value as it is. If we take this on the other side, it will become Cp minus Cv equals to P plus del U upon del V at constant temperature into del V upon del T at constant pressure. Consider it as a equation number 6. Now we have to consider another experiment that is also very famous experiment, although I have not discussed it until now. We will see this experiment in our future lectures. So we will consider the result from that experiment that is done by Jules, the scientist Jules, and known as Jules Experiment. What it says that for an ideal gas, while we open the stopcock, there is no work done, right? And at the same time, there is no heat transfer took place. These two were the conclusion from this experiment. And according to that, if we consider this and this, what will happen? Del Q is 0, no heat transfer took place, equals to du plus 0, because dw is also 0. So according to first law of thermodynamics, we can write dq is equals to 0, that is equals to du plus dw. So in place of dw, it will be again 0. And from that equation, we get du equals to 0 ultimately, right? So this du is 0 even if we change the volume of system, okay? But the condition is we need to consider the temperature should be constant in that system. And in that time, there will be no change in internal energy with respect to volume change. So we can write in mathematical form del U upon del V at constant temperature is equals to 0, right? Putting this value and we will get one more value, because here if you see one value is something like this and another value is this also, so we have to put some values. Now we consider the ideal gas equation, and that is given by PV equals to RT if we differentiate it with respect to temperature, because the second term is with respect to temperature. So if we consider the differentiation, what will happen? P into del V upon del T at constant pressure equals to R, because T will be 1. The differentiation of T will be 1 because it is with respect to temperature only. So this is our equation 7. Now putting these values in equation number 6, what will happen there? Equation 6 is something this: Cp minus Cv equals to, this term will be 0 already. So what will happen? P into this term, and this term we have already calculated from equation 7, that will become R plus 0. So Cp minus Cv equals to R plus 0, or we can write it R. Cp minus Cv is equals to R. This formula is very important and known as Mayer's relation. It will be used several times. In fact, this we have already used while we were deriving some equations in our last lectures, right? So this is our first thing. Now we will consider a specific heat of a gas for a reversible adiabatic process. Now what is adiabatic process? Where no heat is exchanged between the system and surroundings. That means del Q should be 0. Now from equation 3, which we have already derived, equation 3 will become 0. We already put the value of del Q as 0 equals to Cv into dt plus bracket P plus del U upon del V at constant temperature into dV, right? If we take it on the other side, it will become Cv into dt equals to minus P plus del U upon del V at constant temperature into dV. Now if we divide it by dV throughout, then it will become Cv into del T upon del V equals to minus bracket P plus del U upon del V at constant temperature, and this is termed as equation number 9. Now we will consider another condition. Let us assume that this is isobaric process. For the isobaric process, the volume coefficient of the expansion is given by alpha. That actually we have not derived yet, but from the definition of isobaric process and from the expression from the isobaric process, the volume coefficient can be written as alpha equals to 1 upon V into del V upon del T at constant pressure. If we take this V on the other side, it will become alpha V equals to del V upon del T at constant pressure. And we already have derived Cp minus Cv equals to P into del V upon del T at constant pressure. Okay. Now, if we divide this equation by this equation, what will happen? It will become Cp minus Cv upon alpha into V equals to P. This term will cancel out with this term, and we get the final equation that is given by Cp minus Cv upon alpha V equals to P. This equation is important and is valid for any adiabatic reversible process. Okay. Now we will see the second application of the first law of thermodynamics, that is for isochoric process. What is an isochoric process? The process where we keep the volume constant. The volume of any system remains constant and there will be some change of state, then that process is known as isochoric process. And because we have already seen volume is constant, that means dV will be 0. And if dV is 0, the total work done will be equals to 0. Why? Because dW can be written as P into dV. That means we can write del W is equals to 0. So that means from the first law of thermodynamics, which is saying dQ is equals to du plus dW, will become dQ is equals to du. From this expression, this you have to remember for the isochoric process. We can apply this for the several numericals. We have to put the conditions in numericals. So that means you need to remember this, or if you consider some logic, then you can also define it. This expression is important because we can define the definition of internal energy. We can define the change in internal energy of the system in terms of supplied heat. Okay, so how we can define? The increase in the internal energy of a system is equal to the heat absorbed by the system at constant volume. Here volume remains constant, so the work done in isochoric process is 0, right? These 2 points we can conclude from the first law of thermodynamics. Now we will go to third process or third application we are considering here as isobaric process. Isobaric process is where the pressure is constant. So any system which is going from one state to another state, when the pressure is constant, that process is known as isobaric process. Here let us assume that Q is the amount of heat that is absorbed by a system at constant pressure, because this is the condition for the process. And let us assume by supplying this Q heat, the volume is changed from B1 to B2. Of course, that will increase because we are giving some energy from the outside. That means the volume will increase if we keep the pressure constant. Then from the first law of thermodynamics, we can write Q equals to, there is a change of state, so that means internal energy will be changed. We can write U2 minus U1 plus W. And what is W? W is given by P into dV, and dV is the volume difference from the first state to second state. We can write it V2 minus V1, right? Now let us collect two terms, the equation the terms corresponding to state 1 and terms corresponding to state 2. What will happen? It will become U2 plus PV2 minus U1 plus PV1. So this is corresponding to state 1, this is corresponding to state 2, and together we can write it as a quantity H2. U2 plus PV2 equals to H2 minus U1 plus PV1. Similarly, we can write H1. So that is a new term which is known as enthalpy of the system. From this equation, Q equals to H2 minus H1, we can conclude that the total heat that is absorbed at constant pressure is equal to the increase in enthalpy of the system. This term is defined here as a new term. We will see it in detail in our next few lectures. Okay, right now we can consider this is the term which is defined as enthalpy of the system, and the heat supplied is equal to the increase in enthalpy of that system. Now let us go for the last process of today's lecture, or we can say last applications of the first law of thermodynamics. Of course, there are several others, but for example or for your understanding, we are assuming these processes in your course. So the adiabatic process, as I told earlier also, adiabatic process is where the heat exchange is 0. There is neither heat can enter to the system nor the heat can exit from the system. Okay, in this process, because there is no exchange of heat, Q will be equals to 0, right? from the first law of thermodynamics, Q equals to U plus W. So we can write 0 equals to U plus W, or we can rearrange it and can write U is, we are defining it internal energy change, so we can write from one state to second state U2 minus U1 equals to minus W, right? Now we can consider the process something like this. It is going from point A to point B. The states are defined by point A and point B on this PV curve. Here the coordinates for state A is given by P1, B1, T1, and corresponding internal energy will be given by U1. Here, when the volume is increased, the pressure is continuously decreased, and the coordinates of point B or state B is given by P2, V2, T2, and the corresponding internal energy of that system at this state will be given by U2. Okay, here it is important that T1 should be less than T2. T1 will be less than T2, right? Now we know for adiabatic process, for an ideal gas, U2 minus U1 can be written as Cv into dt. That we have already seen when we derived the first expression today, right? So we can write U2 minus U1 equals to Cv dt. If we compare these two equations, we get the work done is equals to minus Cv into dt. So here W is work done by the system. Okay. Now from here we can consider one conclusion. If we look at into this equation, we can say that if any system expands adiabatically, you see here the volume is getting increased, so that means expansion is taking place, and we are considering this adiabatic process. So if a system expands adiabatically, its internal energy decreases. Why it is decreasing? Because if you see here, U2 minus U1 is a negative quantity. That means the internal energy of the system is decreasing, right? On the other hand, if we consider it on the other side, if we allow the system to compress, if we compress the system adiabatically, then what will happen? The work done will be negative, right? W will be negative, and that time this expression will become U2 minus U1 equals to minus bracket minus W, because W is negative. In that case, what will happen? U2 minus U1 will be plus W, and that will be a positive quantity. And because of that, when the system is allowed to compress adiabatically, the internal energy of the system is increased. Okay, these two conclusions we can get from these equations. The value of work done can be given by this, and the internal energy, whether it is increased or decreased, can be given by this equation. Okay, now we will derive an adiabatic equation for a perfect gas. We have already derived three different equations that were giving the relationship between pressure and volume, pressure and temperature, and volume and temperature. So we will do it again here, but this time we will use the first law of thermodynamics. So for that, let us start. Let us assume 1 gram of working substance. Working substance can be ideal gas that is perfectly insulated from the surroundings. That is, insulated means no heat exchange is possible between the system and surroundings. Let us assume the external work done by gas is del W, and del W can be written as P into dV. Now from first law of thermodynamics, we can write 0 equals to du plus P dV. Del W is P dV, dq is 0, so we can write it in this way. Now how the gas is working, how the external work is done by the gas, where it is taking the energy from. It is taking the energy from its internal energy. Okay, if it is taking the energy from internal energy, what it will do? It will reduce the temperature of the gas by, let us assume, by a quantity of dt. So what will happen? du will be equals to Cv into dt, that we have already derived in our first expression today. So that du will be equals to Cv dt. If we put the value in this equation, it will become Cv dt plus Pdv equals to 0. Now from ideal gas, we already know Pv equals to RT. Okay, if we differentiate it, we will get P into dV plus V into dt equals to R into dt. Okay, now, in this equation, the value of dt from here, we can get p dv plus v dp upon small r. Okay. Now, putting this value of dt in equation number 2, it will become cv into p dv plus v dp upon r, bracket close, plus p into dv should be as it is. Okay, now that is equals to 0. If we solve it, it will give us cv into pdv plus vdp plus r into p into dv equals to 0. Okay, then from the Meier's equation, we already know that Cp minus Cv is equals to R. Now putting the value of R in our previous equation here, the equation will become Cv into P into dV plus Cv into V into dP plus Cp into Pdv minus Cv into Pdv, right? Now if you consider this term and uh, this term are equal in quantity, but with the negative sign. This is positive and this is negative, so these will be cancelled out. The remaining term will become Cv into Vdp plus Cp into Pdv equals to 0. Now, if we divide this equation, whole equation, by this term Cv into Pvv, what we will get? We get Cp upon Cv into dV upon V plus dP upon P equals to 0, and we know that Cp upon Cv is given by gamma, the ratio of specific heats of gas at constant pressure and constant volume. So we are putting this as gamma here, gamma into dV upon V plus dP upon P equals to 0. If we integrate this equation, what we get? Gamma into, gamma is a constant, so gamma into this term will change to log V. If we integrate this, it will become log V plus this will again become log P. So the final term will become log P plus gamma log V equals to constant. If we combine it, because these are two log terms, we can take gamma at the power of V, so we can write it log PV to the power gamma equals to constant. Because since this is the constant, we can remove log and we can write directly PV to the power gamma equals to constant. This is the equation which we have earlier derived and gives the relationship between the pressure and volume during the adiabatic process, and this law is known as Poisson's law. We can represent this equation in terms of pressure and temperature and volume and temperature by using ideal gas law. So from ideal gas law, we can write PV equals to RT. Putting the value of P in this equation, we get R into T upon V into V to the power gamma equals to constant. We can rearrange it. When we take V to the top side, then it will become RT into V to the power gamma minus 1 equals to constant. Since R is again a constant, we can take it into the constant, and the final expression will become T into V to the power gamma minus 1 equals to constant. That is our equation number 5, and that is the second relationship for an adiabatic equation. Now, P and V relation, T and V relation, the third relation is remaining between P and T. So we have to replace P equals to RT upon P from the ideal gas equation. In this equation, we can get RT upon P to the power gamma into P equals to constant. Okay, we are putting the value of V in this equation. So it will become, after rearranging, we will get R to the power gamma into T to the power gamma divided by P to the power gamma minus 1. Okay, we are getting this. Now since R is constant, we can take it on the other side. The final equation we get T to the power gamma minus 1 upon T to the power gamma equals to constant. This is the relation between P and T. So these are the relations for an adiabatic process of a perfect gas. We are considering it for the ideal gas. So these all are the applications of first law of thermodynamics. Likely we can apply this first law of thermodynamics to many other applications also, but here we will see only these four. Now we will do some exercise to check our knowledge, what we have learned today. We have studied the applications of first law of thermodynamics, and according to that we will judge the knowledge. The first question for you is, Mayer's formula is given by Cp minus Cv equals to 0, Cp plus Cv equals to R, Cp minus Cv equals to R, or none of them. So if you recall our today's lecture, or we have already used this formula several times before, you know that Cp minus Cv is equals to gas constant. So the right answer for this question is option C. Now the next question is related to adiabatic process. For an adiabatic process, dV is 0, dP is 0, dt is 0, or dq is 0. So these are giving the changes in, first one, volume, change in temperature, change in pressure, and change in heat. So for adiabatic process, how to define? Adiabatic process is the process where no heat exchange is allowed. No heat exchange is allowed means heat remains constant. Heat remains constant means dq should be 0. That means the right answer for this question is option D. dq is 0. Now we will come to next question, and that is, in an isochoric process, volume is constant, pressure is constant, internal energy is constant, or none of the above. What is isochoric process? Where the volume of a system is constant. So the right answer for this is option A, volume is constant. The next question is also related to the isochoric process. So the question is, for an isochoric process, which statement is true? dq is equals to du plus pdv, dq equals to dw, dq equals to du minus dw, or dq equals to du. So for isochoric process, we have already seen here that volume is constant. Volume is constant means dv is equals to 0, and dv equals to 0 makes total work as 0. That means from the first law of thermodynamics, dq equals to du plus dw, dw is 0, then dq is equal to du. That means the right answer is option D, dq is equal to du. Okay, let us move to the next question. The enthalpy of a system is given by H equals to U plus PV, H equals to U minus PV, H equals to U minus Q, or none of the above. So we have already defined the enthalpy when we were deriving the equation for isobaric process. There the pressure is constant, and there we have defined that Q is equals to H2 minus H1. So for the state 2, it is U2 plus PV2, and for state 1, it is U1 plus PV1. Right? Now, if we look at our question, what it is asking, the enthalpy of a system is given by H equals to U plus PV. Okay, so the right answer is H equals to U plus PV. Option A is the right answer of question 5. Now let us go for the next question, that is, in an isobaric process, the temperature is constant, pressure is constant, volume is constant, or heat is constant. So isobaric process is defined as a process where the system changes one state to another state by keeping pressure constant. So that means the right answer for this question is Option B, pressure is constant. The next question is related to adiabatic process. So in adiabatic process, this process occurs at constant. What is the variable that kept constant in adiabatic process? Heat, temperature, volume, or pressure? Of course, adiabatic process is the process where no heat exchange is allowed. That means the heat is constant. So the right answer is option A. The heat is constant during the adiabatic process. Let us come to the next question, which is related to 0th law of thermodynamics. So 0th law of thermodynamics is kinetic energy of gas molecule is zero. Ideal gas does not contain molecules. C option, absolute zero temperature cannot be attained. And the last option is if two systems are in thermal equilibrium with third system separately, then they both are in thermal equilibrium. Yes, the option D is right. According to 0th law of thermodynamics, if two systems they are separately in thermal equilibrium with the third system, then these two systems should also be in thermal equilibrium. We have seen the example of two boiling water cups and the thermometer. When we put the thermometer in first cup, it increased the temperature, the reading is increased up to 100 degree, and when we put this thermometer into the second cup, the temperature reading remains constant. That means the thermometer is in thermal equilibrium with the both cups, and that will allow that the two cups are also in thermal equilibrium. So that is the 0th law. So option D is the right answer for this question. Let us go to the next question. The transfer of heat from a body at low temperature to a body at high temperature, is it possible? Okay, the options are: it is possible by keeping both bodies in contact, it is impossible, it is possible by doing some external work, and none of these. So what do you think? The heat can be transferred from the low temperature to high temperature? No, it does not happen spontaneously. That means if we do not supply any heat, it will never be possible. Okay, but we can transfer the heat if we do some external work on the system. So the right answer for this question is option C. It is possible by doing some external work. And the last question for today is related to specific heat. Specific heat at constant volume is given by del Q upon del T at constant V, del Q upon del V at constant V, del U upon del T at constant V, and del U upon del V at constant V. So the specific heat, the definition says the answer A is right answer. The change in heat for the unit change of temperature is given by the specific heat at constant volume, and that is true for the unit mass of the system of the specimen. Okay, so this is all for today's lecture. We have seen several examples, several applications, and I hope you have understood everything from today's lecture. You can apply this law by yourself for the other applications also. Thank you for listening. Thank you for your patience.